We'll just wait for some time and then get started. Okay. Okay, so welcome to this fifth class on electromagnetic theory. And so I'm a PMR fellow here in IISc and I'm doing my PhD here. And this class is a part of the PMRF ship that we are trying to do. And this course is about electromagnetic theory. And as you have seen in the last few classes, this is about basically we started with electrostatics. We discussed like Coulomb's law and the basics of you know vector algebra, how vectors and scalars are characterized. Okay, so divergence, curl, and all that we discussed. Then we moved to Gauss's law, which makes use of the symmetry that is there in the problem and helps us to helps in the calculations of fields and potentials and all that, and gives us this relations which relates the divergence or curls of electric field with the charge densities or the potentials and so on. So all those relations we discussed. And then we talked about Laplace equation, which was like how do one find the potential and using the Laplace equation, and how to use the boundary conditions. How does the the potential expression, how does it relate to the charge densities and all those relations, starting from Laplace equation, what is uniqueness theorem, and how one can use the uniqueness theorem, which again comes from a property of the harmonic functions that means the solutions of Laplace equation has certain properties which led to the uniqueness theorem. And from there, we could actually get to the method of images. That's what we discussed in the previous classes. So today we'll be, and then we move towards magnetostatics, right? So today we'll be talking about magnetic forces and, what happens when you have a magnetic dipole. How do one find the field due to a dipole? Okay, how does the medium property of a medium, what is the magnetic property of the medium, how does it affect the fields or the forces that one experiences, so all that, right? So that's about today's class. Okay, so let's get started. So we are starting with uh, magnetic forces, right? So as we discussed in the last class, we saw that if you have constant charges, that results in electric force, while if you have a okay, so we are just starting now, and today we'll be talking about magnetic forces and magnetic dipoles, the field due to magnetic dipole, how the magnetic properties of a medium affect the fields, all that. Okay, that's about today's class. So to start with, we saw that in electrostatics, if you have constant charges, then that results in a electric field, and we could see how the charge distribution, like the rho or the sigma, how are they related to the field and the potentials, right? We did that in electrostatics. And then we saw that for magnetostatics, if you have a constant current, that results in a magnetic field. Okay. how the direction of the magnetic field will be, we saw that it comes from the Biot-Savart's law that we had discussed in the last class, which says that, if you have a current in a certain direction, okay, and then so suppose the current is in this direction and you want to find the field here. So there is a cross product between the line element along the current and the direction from the current element. Okay. And the cross product gives us the direction of the magnetic field. And you have this entire formula of Biot-Savart's law. With that, you can actually find field due to a infinite current carrying wire, circular wire, and all that, right? That's what Biot-Savart's law can be used for. Right. Now, there's this very well-known, what do I say? A simple rule, okay, which can be used to find the direction of the field. So if you have a current along the thumb, we know that all the four fingers, if we hold it like this four fingers gives us a direction of the magnetic field lines, right? So it looks like this. So if you have a current carrying wire, this is how the magnetic field lines will, right? So one can use this thumb rule, okay, to find the direction of the fields. And if you are finding it difficult to understand how to, place your thumb and look into it, then you can actually do the cross product. Okay, look into it mathematically, doing a cross product between the line element along the current and the direction where you want to find the field, the position vector in that direction, right? So that gives us the direction of magnetic fields. Now, what was seen is that if you have two wires, okay, so like here you have two wires carrying some current, it was seen that when you bring the second wire close to the first wire, this first current, this wire, second wire, experiences a force because of the first wire. Okay, so that means what this is telling us is that when you have some, so what is current? Current is basically charge flowing, right? So that means when you have some moving charges, they experience some force because of the magnetic field that is generated by this wire. Okay. How that force, like what that force is given by this relation here. So it tells us that if you have a charge Q moving with velocity V in a field B, then the force that it experiences is given as Q into V cross V. So if you now look into the total charge, which like if you have both electric and magnetic field, it will be given by this Lorentz force, which is given as QE plus V cross V. So this is your electric force, this is your magnetic force. Important point is that the magnetic force is perpendicular to the direction of motion, right? It's V cross V. So that means F is perpendicular to V and F is perpendicular to V. So because it's perpendicular to the direction of motion, the work done, if you want to find F dot dl, basically dl, which is the direction in which the charge moves, that is in the direction of the velocity, right? And your force is perpendicular to it, so you end up getting zero. So that means magnetic forces do no work, okay? And basically, this is the relation which tells us in what direction the force will be, right? So if you have a current in this direction, this current carrying wire will have a field. So like if I try to do it, it's like current in this direction. So the magnetic field lines are into the page. And then if you have another current carrying wire where the velocity is in this direction, then the force will be attractive. It will come close to the wire, right? So this was something interesting, which tells us that moving charges experience a net magnetic force. So that means now if you look at this current carrying wire, you can actually write it as something like this, where you define a term lambda, which is the charge per unit length, like how much it's moving, and that into V, that is your net current that is flowing per unit time through a region, right? So that this is the net current. So you can basically rewrite this expression. So if you want to find the magnetic force on a segment of current carrying wire, so you have to find the dq charge that is there in that segment. And that segment, the charge is given as lambda into dl. So if the charge per unit length is lambda, then lambda into dl will be your dq. It's moving with charge velocity v. So again, lambda v, you can take it up as your net current. So you get an expression like this. So basically, this is how your magnetic force looks like for a current carrying wire, right? So if your current is constant, you can take the current outside the integral. So this is how it looks like. So what this is telling you, that the magnetic force is perpendicular to the line element of the current carrying wire. Okay, so whatever your wire is, the current is flowing through that. The magnetic force should be perpendicular to that, and it should be perpendicular to the field that this wire produces, right? So this gives us the direction of the magnetic forces. So now based on that, you can also have surface charges, right? Initially we discussed about, here we talked about line charges. You can also have surface charges. So something like this, where you have basically surface currents. So currents flowing through a surface. So what you can then do is you can define this small perpendicular line segments like DL perpendicular, which is basically perpendicular to the direction in which, basically your uh, surface current is. So now, if you break your entire surface into such small elements, you can say that if your surface charge is sigma, sigma is the charge per unit length, the unit area, and the velocity is v, then the relation is the surface current can be defined as sigma into v. Okay, and if you break it into such segments, you can actually do integrals, right? So k is di by dl perpendicular, right? Because k is the surface current density into dl will give you the amount of current that is flowing through this segment, the selected segment, right? So now for, just you can translate the expression of your magnetic force, but now in a surface integral. Basically, replace dq by sigma dA. Okay. So again, you get an expression like this. So this is your expression of magnetic force for a surface current density. Okay. For a volume current density, again, you can define a region like this. Okay. So then you would say that J is nothing but the volume charge density into the velocity. Okay. And what is the current that is flowing through this segment? That is nothing but J into this area element, right? And if you replace dq as rho d tau, then this is the relation that relates the volume current density and the field with the magnetic force. Okay, so that's the basic relations that are to be used if you want to find magnetic forces. Okay, now there can be questions like this where you have a current flowing down a wire of radius a, current is I. Now, if it is uniformly distributed over the surface, what is the surface current density K, right? So you have a wire, the radius of the wire is given. That means you know the area, right? So you have to understand. So here, suppose if this is the wire, you are talking about this perpendicular area, right? You're not talking about the curved surface area. You are breaking your segments along this. So the area of interest is this area which is perpendicular, right? So that means for a wire, the effective area will be this, right? Given by this cross section. So that means now you can write it as something like this, right? So if you're here, if you have surface current density, basically not volume, but surface current. So that means now you have to look at, what I mean is you have a wire. So if it was a volume, that was different, right? Now it's a surface current. So basically your current is flowing through the surface. So you have to break the current into small segments. How will the segments be? You can break it into small segments like this. So this length, how much will this length be? Right? The total length. So if you look at this region, the total length is nothing but the circumference of your circular cross section, right? So that means now you can write K as the total current I divided by the circumference of the wire. Okay, so that's how you find K. If you have to find J, then it will be I by. So suppose if you have to find J for this condition where you have a uniform current, then it will be I by pi a square. Understood, right? So that's how you define your surface current density or volume current density. Now, the next question says that if it is distributed in such a way that the volume current density, so that is J, is inversely proportional to the distance from the axis. What is J? So it is telling you that J is inversely proportional to S. S is the radial component. Okay. So then what is the total current? Total current is nothing but J into dA, right? So basically now you are looking at something like this. Okay, something like this. So here it is said that your J is inversely proportional to the radial component, right? So if you want to find the total current, what will you do? You will have a J, you will multiply it with such small current elements, and then do an integration over the entire region, right? The entire region. So that's what has been done here. So I is J dA. So now J is inversely proportional to S. So you write it as 1 by S. S is nothing but R, okay, the radial component. And then what is your area element? You can take it as S ds d phi, and you have to do an integration over phi, which goes from 0 to 2 pi, and you have to do an integration over S, which goes from 0 to A, right? The radial component goes to ranges from 0 to A. So that means you end up getting this. So that means you now know what is your proportionality constant alpha. So alpha is I by 2 pi A. So once you know alpha, you basically know how your J looks like. J is I by 2 pi AS. Suppose if it was asked that J is constant, so then what would happen? Basically, this term will not be there. That's all. You will have a constant quantity here. The entire process will still be the same, right? So based on the functional form of your J, you can do all these kinds of integrations to find the net current, the net charge density, net current density, and all of it. Okay. So till now, what we have learned is that this is how you can write an expression of magnetic force for a line element. This is for a surface current density, and this is for a volume current density. Okay. Now, force of attraction between two long parallel current carrying wires a distance d apart. Okay, so this is something we just discussed. Now let us look into it in details. So it was seen that when you have a current loop like this, when you have currents flowing in opposite directions, like here, currents were like if you have such wires, they were seen to repel each other. Okay, while if you had currents flowing in the same direction, it was seen that they attract. So how can we understand this, right? So for this, if you can consider two wires, I1 and I2 at a distance d apart, we want to find the force of attraction. Also look at the direction of the force, okay, whether it's attractive or repulsive, where it is attractive, when it is repulsive. So for this, what is the first thing that you have to do? So suppose you want to find the force on the second wire because of the first wire. So you have to find first what is the field due to the first wire at the location of the second wire, because it is the field that is causing the force. So you need to first find the field due to the first wire. Then what do you have to do? Then you have to see what is the current, because that is a measure of what charge is moving with what velocity. And you have to look at the direction of the current. And based on that, rest is known, right? Rest we will use our formula that we just discussed. Okay, and that will give us the value of, but basically the Lorentz force formula that will give us the value of the net force. So for this, for a current along a line, you know this is the relation that gives the expression for the magnetic force. Now, what is the field due to the first wire at a distance d, where your second wire is? It is given as mu 0 I by 2 pi t. Okay, so how do we derive that? This comes from Biot-Savart's law. There are also easier ways of doing it that we will discuss as we proceed. But one can basically do a Biot-Savart's law, where if you have an infinite wire, this is what the field looks like. Okay. So now the force will be, what is the current flowing through the second wire? I2. And you have a field, and you take small dl elements along this current carrying wire. So basically, this is your force on the second wire, right? So now if you want to find force per unit length of, like, what is the force per unit length on the second wire? Basically, you divide by the net length of your second wire. So you end up getting this, right? So this is your expression of force per unit length between two current carrying wires. Okay. Now, if the currents are in the same direction, this is an attractive force. Okay. If they were in the opposite direction, you would get a minus here, which would mean that it's away from the wire. So it would be a repulsive one. Okay. How to understand that? It is look closely at the direction, because this is a very important for us to understand and be able to locate the direction. Okay. If you have any doubt, feel free to ask me. Okay. So here, suppose this is the current carrying wire. What will be the direction of the magnetic field? The magnetic field for a current carrying wire going upward in Z. So if you say this is your X, this is Y, and this is your Z. Okay. So for a current flowing along Z, what is the direction of the field at this location? Can you tell me how? Why are we getting the field along minus X? What is the relation that is giving me the field along minus X? This is something we have already discussed. Okay. What is the relation that tells us that the field for this wire has to be in the minus X direction? I'm just going into it because many a times people get confused with the directions. Okay, so the vectors are very important to understand. So you have your field along Z, okay, and your position vector. Is there a message? Okay, and your position vector, the field point location is along Y, right? So basically, now if you use your initial formula of Biot-Savart's law, this tells us the direction of the field is perpendicular, is given as dl prime cross r. So dl prime is the direction of your current element, and r is the position vector direction, right? So for this case, you would have the directions as z, this is along z, cross y, right? So that's why you get the field along minus x, z cross y, that is along minus x. So now once you know the field is along minus x, now you have to find the direction of the force. So what is dl? dl is the direction of your current carrying wire, okay? And the direction of the field is along minus x. So basically the cross product is between z and minus x. So that gives you the direction is along minus y. So this is your direction of force. What it is telling you? Minus y. Minus y means attractive, right? Suppose the current direction is reversed. What will happen? This will be minus z, right? So that means the current, then the direction will be in positive y direction, which means repulsive, right? So that's how you have to look into the cross products and be careful about the signs, okay? Attractive, repulsive, and all. Okay. So similar types of, idea can come up in questions like this, where you have two infinite straight line charges, lambda, distance d apart, moving at a constant velocity v. So basically, it's same as the last case, where the current will be given as lambda into v, right? Now, how great would v have to be in order for magnetic attraction to balance the electric repulsion? Okay. So first, let us try to find what is the magnetic force. So this is same as the last question, where the current is now given as lambda into v. So we know how to find the force, right? So the force will be force per unit length. If you have to find, it is nothing but mu0 by 2 pi lambda square v square by d. This is your magnetic force. Okay. So this is nothing but writing this relation, replacing I1 and I2 by lambda into v, right? Now, it is asked in the question that what should be V so that the magnetic force balances the electric repulsion. So for this, now what we can do, you have charge. So you can try to find what is the field due to this charge, right? So the field would be given as 1 by 2 pi epsilon naught lambda by S. This comes from our well-known Coulomb's law or, Gauss's law, known thing, right? This is we have already discussed. Now you know the electric field. So now if you want to find the force per unit, uh, electric force per unit length, it's nothing but multiplying this by lambda, right? Q into E. So this is your electric force. So if this has to balance, that means the ratio has to go to 1. So if you do that, we get a value of V, which turns out to be the velocity of light. So this is telling you that this charge that you have here has to move with velocity of light for the electric and magnetic forces to balance. Why this question is important is this tells us that that is never possible, right? So things move. What are the things that move with the speed of light? So for that you have to have photons which are massless, right? Electrons cannot move at that speed, right? So that already tells us that electric force always dominates in these cases. Okay. So it highlights the limitation of classical physics that only massless particles travel at the speed of light. So real line of charge made of material particles, okay, they there the electric force will always dominate. Okay. That directly comes from this exercise we just did. Okay. So now let us take a step ahead and talk about divergence and curl of B. Okay. So we know that for a current carrying wire, the magnetic field is given as mu 0 I by 2 pi S, where S is the distance from the wire, right? So now if you want to find, yeah, and this is how the field lines look. You can also get it from the thumb, right? So if this is the case, now if you want to do a line integral over some surface, so if you just take a circular, loop like this, and you want to find the line integral along that closed loop, how will it be? It would be given by this relation. And now when you do the line integral of dl is nothing but the circumference. So you end up getting u naught I, where I is actually the current of this wire, which is enclosed within this loop that you have considered, right? So this gives rise to a very important law, which is the Ampere's law, which is analogous to what we had for electrostatics, where we had the Gauss's law, right? We had Coulomb's law, and then we had Gauss's law, which made use of the symmetry and gave us a simpler relation that relates with the charge that is enclosed within a volume or within a closed loop. So here again, we now have a similar analog for magnetostatics where we have Ampere's law. So for this, it might not again be a circular cross, line element. It can have any kinds of, you can choose any path. Okay. Why? Because now you can look at the general vectorial form, and you can say that what is the field due to a current carrying wire? It is given by this relation, right? So now if you take any line element dl, when you will do the dot product b dot dl, only the phi component will survive, right? And ss will cancel. So when you do an integration over phi ranging from 0 to 2 pi, you again end up getting the same relation. That means the loop does not need to be a circular loop or something. It can be any loop as long as it encloses this current I. Okay, this will hold. So again, you can use the divergence theorem and you can rewrite Stokes theorem, and you can rewrite from the line integral to a surface integral. Okay, so if you do a surface integral, you can write the current as JdA. So basically, now you can get a relation between the curl of B and the volume current density. Okay, so this is your, you can say, the differential form of your Ampere's law. Okay, while this here is your integral form. Okay, so this is the equation of curl called the Ampere's law, and you can also write it in this form, which is the integral form. So basically, if you know the current enclosed, you can try to find the curl of B, and if which will come again later, that for any vector to be properly defined, you need to have the information about curl, you need to have the information about divergence. For magnetic fields, because there are no monopoles, the divergence goes to 0. So you know that the divergence is 0 because no monopoles exist. And from this relation, you know how the curl changes. So if you know curl and if you know divergence, basically you know the field. Okay, so you can find the magnetic field. So for a current carrying loop again, so whatever we had done with the Biot-Savart's law, the derivation for an infinite wire can also be done with this using the Ampere's law by considering an Amperian loop at a distance s. So the current enclosed is I. So on this side you have mu naught I. And if you do the line integral, you will end up getting B into 2 pi s. So this gives you again the same formula of magnetic field for an infinite wire. Okay. So this is what we have just come up with. Coulomb's law, and then we got Gauss's law. The analogous thing is Biot-Savart's law, and then Ampere's law. Okay. Later we will see that there are certain modifications in the Ampere's law that came up. Okay. Now, based on what we have discussed so far, let's try to answer this question. Okay. So find the magnetic field of an infinite uniform surface current K flowing over XY plane. So this is your XY plane, and this is where your current is flowing. The direction of the current is given by this arrow, as you can see. So there's this steady current flowing through the sheet, and you have to find the magnetic field. So what is the field below? What is the field above? You have to find those expressions. So what is the first thing that has to be done to answer this question? As you can see here, you have to consider an Amperian loop. This is similar to when we talked about capacitors and this surface charges over a plane. We used this Gauss's law, right? And we had this Gaussian surfaces constructed. So similarly here, you will construct an Amperian loop. Okay. So for this, current carrying sheet, you will have some field somewhere above. So some B here and some B below, right? And you have to do a line integral over this Amperian loop, and the length of the loop is given by L. Okay. So if you take this width to be significantly small, then what is the net current? That is, the current is only along this plane, right? So that means the current enclosed will be given as K into L. Basically, this entire region you can break into small line segments and then do an integration over the length that is given. So the net current enclosed is K into L. So the right hand side is clear. You have the current enclosed in the loop, which is given as mu naught K into L. Okay. And the left hand side, which is the line integral, is given as 2 into B into L, right? Because the magnetic field lines has to be, when you're doing a line integral, you have to take into account the one that is parallel to this element, so that only that term will survive. So you'll end up getting B into L and then again another B into L. So 2BL. Okay. So from here, you can say that the magnetic field above the surface looks like this, magnetic field below the surface, vice versa. So magnetic field below looks like this and above looks like this, right? So this value is independent. It already tells us independent of the distance from the plane. And it's similar to how initially for a, plane with a surface charge, infinite plane, it did not depend on how far we were from the plane, right? It was a constant value. So similar things come up here. You have to be careful about how you get to this sign. Okay. So basically, when you're finding the magnetic field, again, you're doing a cross product. Okay. So suppose here, the direction of the current density is along X. Okay. So anywhere in the minus Z direction, that is below the this plane, you'll have the cross product will be between K cross minus Z, which is X cross minus Z, right? And above you will have X cross plus Z, anywhere in the above the sheet of plane. So that's how basically you are getting plus Y and minus Y. Okay, that's how the sign comes up. So another kind of question could be to find the magnetic field for a long solenoid, and this is a very standard result. So basically, what is a solenoid is you have this closely wound turns of wire through which current flows. So if you have n such turns per unit length, and the radius is r, the steady current is I, then you can again basically have something like this. So you can, because the current is flowing through the wire, you can think of it as something which has this surface current density given as K. And then you can again consider a typical Amperian loop. Now here you have to be careful about what is the direction of your magnetic field. So for this questions, be careful about making use of the symmetry that you have. Okay. So here the magnetic field cannot be in the phi direction. Why? Because your K is in the phi direction. Here. So magnetic field has to be perpendicular to K and the position vector, right? So magnetic field cannot be along K. So there is no component of the magnetic field along the phi direction. And then, hello? Okay. And then basically, if you look at it, you can also get it from, the Amperian loop, it would enclose no current if you take a loop like that, right? So basically, your magnetic field has to be perpendicular to K. So there is no circumferential or component along phi. So B phi is 0. There cannot be any radial component which comes from the symmetry of the question. So if you change the direction of the current, your magnetic field is expected to change. But if you have radial component, that will not get changed just by changing the current direction, right? So that tells us that your magnetic field should not have any radial component. So that means the net magnetic field is only along the axis of your solenoid. Okay. So now what you can do is basically you can consider loops. Okay. Something like this. So anything for, in order to find the field outside, somewhere outside, you can consider a loop like this. And as you can understand, it will enclose no net current. Okay. The magnetic flux lines will enter and leave. So there'll be no net flux. So because of which there'll be no field outside. Okay. If you want to find the field somewhere inside, you can consider a loop like this, where you have, this partially inside the loop and partially outside. So then you can again use the Ampere's law, which will say that the net enclosed current is mu0 NIL. And then the line integral will be given as V into L, because anywhere outside the field will be 0. So only the one that is inside this length will contribute. So B into L, and that will give you the net field. So you can see that the net field inside the solenoid is a finite quantity, while outside it's 0. But you have to understand this we are doing for an infinite solenoid. But in nature, infinite solenoids do not exist. It will be of finite length, finite dimensions, right? So in nature, you will have some fringe effects coming in, some non-uniformities coming in at the corners and sides. Okay. So there will be some non-zero fields that will come up. But if you had an infinite one, then all the field will be concentrated inside. But it's also important to know why it is interesting to study solenoids is because this creates a very uniform field when you go at somewhere here at the center. Okay, so there the field is very uniform. So if you want to create any, region with So like electromagnets, you can use it to make electromagnets to get very uniform magnetic fields. Okay, that's where the applications come in. Now, for such a solenoid, there can be a self-inductance. Basically, what is self-inductance is that this solenoid you have currents, and because of the current, there'll be a field generated. Now, this field lines, right? So you have how much of the field lines? So what is the flux that is going through the solenoid? That's the flux. How is it related to, or what is the proportional relation between the current that is flowing and the flux that is associated with the coil, right? So that proportionality constant is called the self-inductance of the coil. So if you have the number of turns in a solenoid, if total turn is given as N into L, where L is your length of your solenoid and the length concerned, and the magnetic field inside is given as mu 0 Ni. So basically, you know what is the flux, which is nothing but mu 0 Ni into A. Flux is just field into area, surface integral. So this is your flux going through one wire. So if you have n such wires, you can okay, and this flux is proportional to the current that is flowing, right? And that proportionality constant is called the self-inductance of the coil, which is given by this relation here. So you can see this depends on the dimensions of the coil, what is the area, what is the length, what are the number of turns, okay, and the medium that is there. So this formula is for the case where the medium inside the coil is free space. If the medium is something else, the permeability will change. So this mu will be replaced by the relative permeability of that medium. Okay. So basically we'll have mu there, not mu naught. Okay. Okay. So based on that, you can try to answer questions like this, where suppose you have two long coaxial solenoids, current carrying I, but in opposite directions. Now, this one has N1 turns and the second one has N2 turns, and the radius, they have different radii. And so now you want to find what is the field in these three regions, inside the inner solenoid, between them, and outside both. Okay. So for this kind of questions, it's quite simple. So one thing is one can very well understand that there should not be any field outside, right? If this region, if we look at this region, this is outside both the solenoids. So basically, as per our last discussion, the field outside should go to 0. So for this outside both, the field should be 0. Somewhere in between these two, so in this region, between the two, the inner one will not contribute. Why? Because this region is outside the inner solenoid. So this will have no contribution. So in this region, we'll only have contributions from the bigger solenoid. While in the internal region, like inside the inner solenoid, there'll be contributions from both the solenoids. And because they have currents flowing in different directions, the field direction will be opposite. So basically, you will have a resultant which will be given from difference between the two, right? So you end up getting like this. Okay. So mu 0 I Ni minus N into Y, because the direction of current is different. Okay. If it was the same, they would have added up. And somewhere in the middle, you'll only have contributions from the second solenoid, the bigger one, not the inner one. And outside both, everything is 0. Okay. So there can be all kinds of questions which works on similar concepts, where some part of the current will contribute in one and will not contribute on the other. Now, again, there can be questions like this, where you have a large parallel plate capacitor with surface charge sigma and minus sigma, and they're moving with constant speed v. Okay. So what is the magnetic field between the plates, also above and below? And what is the force per unit area on the upper plate, including the direction, and what speed the magnetic force should balance the electric force? So for this question, what is given is this, right? So if you look closely, we have already solved a question like this, right? So some charge density moving with velocity v. This is nothing but having a current, surface current density, right? K is equal to sigma into v. So that means what you are having is you have two current surfaces. So two surfaces with some current density, surface current density given as K and minus K, that K is equal to sigma v. Okay. So it's similar to what we have initially discussed, right? Something like this. But now you have two such things, one plus, one minus, right? And it's similar, analogous to the question of capacitor initially when we had done electrostatics, right? So here, the field in between will be given as sigma naught into K, while outside it will be 0. How are we getting to this point, right? So basically, if we go back to this question, what do we see? So for one such surface, we know what is the field above and field below, right? Now, for another surface having an opposite charge current, the directions will be reversed, right? So because of which, and because it does not depend on how far you are from the plane of the charge of the current, that means anywhere outside, like above or below, basically in this region or in this region, the effects will get cancelled, right? Because the field due to one plane of current will be cancelled out by the other. So above and below, it will be 0. And what will be inside? The field due to this two will be in the same direction. Why? So now you can understand. So suppose if your current density like direction is in the positive direction, so anywhere below, the field direction is in the y direction, right? While for the minus plane, you are above. So again, you have your direction in the minus y direction, right? So the fields will get added up, and that's why you will have a net mu 0 k, where k is sigma p. Okay. Initially, you had mu 0 k by 2, mu 0 k by 2. So when they add up, you end up getting mu 0 k, right? Now, how are we finding the direction? So we are finding it using this relation, right? So that, so if you have to find the magnetic force on the upper plate, so on the upper plate, what is the direction of K? K is sigma V, and that is towards right, which is given by this direction. Towards the right meaning. So if I have to go, sorry, if I have to go in a vector, so why I'm doing this is there can be many questions, okay, many numericals where you have specified values and then you have to find the directions and all that. So that's why I'm just looking at these examples. So suppose here, so what is the direction of K here? So if you have in the K, what is the direction of K? So this is in Y, right? Basically, you are looking at this is X, this is Y, and this is Z. So this is in Y direction. Okay, so K is along Y. What is the magnetic field? That is, so for that you have to find the magnetic field due to the lower plane, right? So the magnetic field due to lower plane will be this value, which is mu 0 k by 2, okay? And it will be into the page. How are you telling that? So basically you are using the relation given by the Biot-Savart's law, basically, right? This relation, okay? So that gives us the direction which is into the plane, that is minus z x, okay? So if this is minus x and this is y, this is along y, so basically now you have to do y cross minus x, which is nothing but z. So that's why your force will be upwards. Okay, so that's how you find the direction of your magnetic force directions. Okay, be careful about this cross products.
Now, again, this question is similar to what we had discussed initially. If you have to balance, so you have to find the electric field. Electric field is given as sigma by 2 epsilon naught, right? So the force per unit area will be given as sigma square by 2 epsilon naught. If you have to balance, again, the speed comes out to be speed of light, which is not practically, physically possible. Okay. So for any physical condition, you will not have the balance between electric and magnetic force. It will always be the electric force dominating over magnetic. Okay. So what we know till now is this. Okay. So we discussed about magnetic forces, how to find directions of magnetic forces. Okay. So we had all those understanding. We talked about the divergence and curl and how one can define the Ampere's law. And from there, we have this relations till now. Okay. This relation comes from the fact that there are no magnetic monopoles. This is the Ampere's law. These are the Cauchy's law, and this comes from the fact that it is it does like the work done by a like in electrostatics, it does not depend on what path it takes, and that gives us the definition of electric potential, right? So just as we have this electric potential, okay, the scalar potential V, you can also define a vector potential A, okay, where you say that B is equal to curl of A. So if you put this relation in the Ampere's law, you get this relation here. Now, here there is a very important point. So it is telling us that, see, for the scalar potential, if we added some constant to it, the field will not get changed, right? So you always have the freedom of adding any scalar constant to the potential, right? So similarly, here for the vector potential, you can add anything to the vector potential such that the magnetic field does not change, right? The magnetic field is the physical quantity that you are measuring. So if the magnetic field remains the same, you can choose any A. Now, that means if you add something to this A, which has a zero curl, that will not change the magnetic field. Okay. So from there comes this idea that if you now have some scalar lambda, and if you do a gradient of a scalar, like gradient of some scalar, then curl of gradient of a scalar will always be zero. So you can always add something like this to your vector potential. Why it is interesting is because now that means you can always add something to your vector potential to make the divergence of the vector potential to go to zero. Okay. Why are we doing it? We'll see that this makes the calculations much simpler mathematically. Okay. See, it's difficult to use, solve this equation. If we get this term to go to zero, what we have is something very similar to the Poisson equation that we have initially described and discussed for electrostatics, right? So that means now you can choose some lambda such that your vector potential, the divergence goes to zero. And then you end up getting del square A equal to minus mu naught J. Okay. How, like, what will be that scalar, like this gradient of scalar that you have lambda? How will you choose that? So basically, if consider that initially your original vector potential was A naught, which was not divergenceless, and then you added something to it, okay, such that divergence of A, this new potential, this is zero. So that already is telling you that divergence of A naught minus of that should be given by del square lambda. Okay. So this relation already tells us what your lambda should be. Okay. And once you know lambda, basically you know A. Once you know A, you can use this relation to now, get an expression of A. So if this is your A, if you know the suppose if you know the volume current density, so you know J. So once you know J, this is nothing but the same Poissonian equation, but now you have three such equations for three different directions because it's a vector. That's the only difference, right? So you can basically, by using this, you can write an expression for your vector potential. And once you know the vector potential, you can always use this relation to find the magnetic field. Okay. So this is how one can define the vector potential. Now, there are also important boundary conditions that one should remember. So similar to the case of electrostatics, okay, where you had all these things like basically that the E above and E below, they have a discontinuity if you have a surface charge sigma. And this is given by sigma by epsilon naught, while the parallel components, they are continuous. Okay. And from there, we get a relation about how to relate the electric field, okay, with the charge density that you have on the surface. So similar to that, you also have some continuity relations for the normal and tangential components of magnetic field. Okay. And this is how it will be. So because divergence of B is zero, you can basically, so the divergence talks about the normal component. Okay. Basically, you can take a such kind of a pillbox kind of thing. Okay. And then if you apply this condition, you'll see that this tells us that the perpendicular components are always continuous. So E above is always equal to E below. While here, because your curl is non-zero, curl of B is not zero, unlike the electrostatic case, right? So because of which, if you take such a line element, okay, closed loop, there you'll see that the continuous, the tangential components have a discontinuity, which is given by the surface current that you have. Okay, so E above by E below for any surface having a net current density K will be given by this relation. The parallel components will have a discontinuity, while the normal components will be continuous. It's equal. Okay, so now this is one of the questions that came up in last year's assignments, and like similar to that. And here you can have questions like this is something which we have already discussed. Okay, so one such example we have already discussed. Let us now look at it in terms of some numerical value. Okay, so here you have two such uh, planes where the surface current density is given, K1 prime and K2 prime, and K basically K1 and K2, and these are defined. Okay, one is a positive one, another is a minus of that. Okay, and then you say that this is the distance between them is given, and you know that the medium inside has some permeability given as 5 times the permeability of free space. Okay, and you have to find how much the auxiliary field is. Basically, now we'll come to that. What is auxiliary field? Auxiliary field is just taking into account the free current that you are providing. It is not taking considering what the magnetization of the system is. So when you have some medium, and like depending on the medium property, if you put it in a magnetic field, it can get magnetized. Okay, so it's not taking into account that magnetic property of the medium. It's just looking into what free current the system has. Okay, what we are applying. So that's the field that we want to find. Okay, so for this three different regions, below the two, in the middle, and above. Okay, so how will we do that? To start with, what do you think the field will be based on whatever we have discussed so far? We have already done a question similar like this. So can you tell me how to approach the question, or like what the values will be? Just any idea? You can also write in the chat box if you want. What will be the field, in this region? Just based on whatever we have discussed so far, we have, I think, done 2, 3 such examples, not with numerical values, but we did discuss similar thing, right? So based on whatever we have discussed, can you try to answer the question? If you get stuck somewhere, like you can ask me. For z less than 0, what the field will be? So somewhere here. Any idea, guys? If you have any doubt, you can ask, or otherwise just try to solve. Remember the fact that for such systems, as we discussed, the direction from the surface does not matter. Okay, the fields do not depend on how far you are from the surface. What matters is what is the direction, okay, and see how the values come up. So I would like to get some, response, because I'm not able to understand if you are following it. Like if there is any doubt, also you can ask. If it's clear, you can also tell me what the answer you think should be. Guys, any problem? Like any like you have been pretty silent all the time. So if you're trying, I'll wait. Otherwise, like I cannot understand whether you are really trying. That's why it's taking time, or it's not that difficult, right? What is the field for z less than 0? That's a very standard question. There's no response, guys. I don't know how what you are following and what not. Anyways, I'll just try to discuss and then see. I hope that you understand. Otherwise, I don't know. Like you have to like at least respond. Okay, so for z less than 0, okay, so if you just look at this surface. So for this surface, z less than 0 for the first surface, okay, what will the field be? The field will be given as mu 0 k1 by 2 y cap, right? How are we getting it? So the field direction is given as the direction of the current element into where we stand, right? So basically the current direction, suppose here, it's x, it's along x, okay? And you are looking at somewhere in the minus z direction. So when you do di cross, basically when you do, you have to do something like this, right? Di or dl, where you have your current element cross, just ignore the spikes, cross r, which is your position vector. So for anywhere in this region below the lower plate, there the direction of k for the current is given as x, and the r vector will be in the minus z direction, right? So that means the field direction will be given as x cross minus z. What is x cross minus z? So that is y, right? X cross minus z is nothing but minus of uh, z cross x. So z cross x is nothing but y. Okay. So this is y. Now for anywhere above, like if you look at this surface, now at the same location, but you're looking at the contribution from the second surface. For the second surface, what will be the direction of the field? So now your di is not x, it's minus x. Okay. So this will be minus x cross again minus z, right? So this minus z or z, this is with respect to your current element, okay, where you are. So with respect to this, you are in minus z direction, right? With respect to this surface, this upper surface, you are in minus z direction. So that's why it's minus x cross minus z, which is nothing but minus y. So that's how you find the direction of your field. So now you know what is B1, what is B2. What will be the net field? The net field will be the addition of the two. So if you add the two, because these two are equal and opposite, it turns out to be 0. Suppose if it was not equal, right, then you would have a non-zero value, which will be given by the difference between the two. Okay? Because they are equal and opposite, they cancel each other. So the net field goes to 0. Clear? Now, what happens to the region between the two? Okay. So now again, for the region between the two, what will happen? So for surface 1, which is again this one, P is in minus y direction, given by mu k1 by 2. This is something we have already derived, right? If you have any question, ask me now. So mu k1 by 2, important is to note you have mu here, okay? Not mu naught. You have mu and you are looking at field. So when you are looking at field, you have to consider the effect of the medium that you have. And the medium has a permeability which is 5 times the permeability of free space, and that does affect the field. So field is given as mu into k1 by 2. Okay. If it was free space, like here, when you were finding the field somewhere here, z less than 0, it was mu naught. Anywhere above, it will again be mu naught because that free space. But somewhere here, the medium property is given as 5 into mu naught. So now you have to replace it by mu. Okay. So mu k1 by 2. Why the direction is minus y? What has changed? So if you again look at this, the direction of your magnetic field is in x direction. But now your position vector, where are you finding the field? You're finding the field somewhere here, right? Above the surface. So the position is in z direction. So you are doing a cross product between x and z, which is nothing but minus y. Okay, so that's why you have minus y. What happens for the second surface? For the second surface, you are still below. So your r vector will be minus z, right? You are still below the surface, but your direction of your current is given as minus x. So the cross product is between minus x cross minus z, which is nothing but minus y. So what has happened? The two fields are in the same direction. So basically they get added up. Okay. So when you add the two, this is what you end up getting. So here you have to be careful about including this mu. Okay. Otherwise your calculations will all go wrong. Because of the medium property, what it is telling you, permeability is telling you how the field lines. So because it's a quantity greater than 1, the field strength will be increased because of the presence of the medium, right? So it's 5 times more. Understood? Now, anywhere in the third region, what will it be? So in the third section, you are above the first surface and above the second surface. So for both the cases, your R, the position vector that you have, will be along Z, positive Z, right? So for the lower surface, the vector, the current direction is along X, the position vector is along Z, the field point is at Z plus Z. So X cross Z. Okay. Now, for the second surface, what will happen? Your current direction has reversed. So you have minus X cross Z, that is Y. So they are now equal and opposite because K1 is equal to minus K2. So what do you end up getting? 0, right? So this is what you end up getting. So because these values are equal to each other, the magnitudes are equal, and based on these directions, you can see that anywhere outside you have to find the difference of the two contributions. And if they are equal and opposite, they'll end up getting like canceling each other. And inside, the fields get added up. Okay. So that's how you have to answer this kind of question. Okay. Now, let us talk about magnetic dipoles. So just as in the last class, if you remember, we discussed about electric dipoles. So where you said that if you have two equal and opposite charges separated by some distance d, we define the dipole moment as q into d, right? So similarly, now if you have a very small magnet, it would have its north pole and south pole. Magnetic monopoles do not exist, so there is no separate north pole or separate south pole. They always stay together. And now if you have such a small magnet, okay, that will have a net dipole moment. So now you want to find the field due to a magnetic dipole. Okay, so how do you do it? So basically, this magnetic dipole is nothing but a small current loop, right? So what you can think of it is that if you have a small current loop, something like this, where the line element is taken as dl along the current carrying loop, okay, the current I flowing is I, and then you want to find the field at a sufficiently large distance r. R is sufficiently large. Okay. So what do you do? So you know that you have to look at from typical Biot-Savart's law. We know that you have to look at the distance between the small line element and the field point, right? And then you have to look at such contributions all throughout the loop. Whatever loop you had, all throughout, you have to look at individual small sections and look at how far it is from the field point, right? And that's how you have to find your uh, field. Then the pins will get added up. So basically, you have to find R. Now, what is R? 1 by R. So what is this? This is just the difference of these two vectors, right? If you do the position vector of the field point and then the position vector for your current element and do a difference between the two, that is your R. So this is how you can write it. This is just doing the difference between the two. So now this term, when R is much larger, okay? So when R is much larger, R meaning this point here, when it is much larger, as a series like this. Okay. So this is a series of Legendre polynomials, as you can see. So that means now if you look at the vector potential for a current loop, this is something we have already derived, right? This is this one. If I go back, we saw this is the relation, right? So now you're using it for this distribution. Oh, sorry. Yeah. So we are using it for this distribution, and it's mu 0 I by 4 pi d L prime, which is basically this small line element, by R, which is the distance from the field point. And then we expand it in terms of the series. Okay. So that means now you get this individual terms. It's a expansion that you get, right? Where the first term is called the monopole, the second term is called the dipole, third term is a quadrupole, like that. Okay. So the first term, as you can see, okay, because it's a closed loop, so the first term will always go to 0. So this again tells us that no monopoles exist. Okay. Now, what happens to the second term? The second term is called the dipole, the contribution coming from the magnetic dipole. Okay, this is the dipole term. So if we just write the dipole term, a dipole is given as mu 0 I by 4 pi r square, r prime cos theta prime dl prime. So this cos theta prime is the angle, right? This angle between the charge element or the current element and the field point. Okay. And now you can do some, algebra, rewrite it. So you end up getting this. This is a very important result. So this tells us that if you have a moment which is defined as nothing but I into the area of your element. So you take a small loop, right? Small dipole moment is nothing but a small current carrying loop. So the area that it encloses into the current, that is your moment. And if you know the dipole moment, what is the field due to the dipole moment at a distance r is given by this relation here. Okay, so this is the field due to a dipole. So now if you use this, like this is the vector potential. So now if you use the vector potential to find an expression for the magnetic field, you have to do a curl of A and you end up getting this. Okay, because the monopoles are always zero, this magnetic dipole moment is independent of the choice of origin. Okay, so for electric dipole moment, whenever the monopole went to zero, it was independent of the origin because there for the magnetic case, the monopole never exists. So magnetic dipole moment is always independent of origin. Okay. And this is your expression of field for a magnetic dipole. Okay. In the vector form, you can write it like this. So M is the magnetic dipole. In the vector form, it has a direction. And then this is the position from the dipole. Okay. R. So suppose if you have a magnetic dipole like this, okay. So you have a magnetic dipole like this, which is pointed along the z direction. So the direction of the magnetic dipole is z cap. Okay. And now you want to find what is the field somewhere here at some point P, which is given by this position vector R. Okay. So here, this is the relation, right? So if you know theta and if you know phi, so in this coordinate system, basically now you are looking at this spherical components, right? So this is r, this is theta, and this is phi. Phi is in the xy plane, theta is from the z axis, and r is the radial direction. So this is how your magnetic field due to a dipole looks like. Okay. So based on in this, you can actually try to put the value of theta and phi and then solve for your magnetic field. Okay. So suppose for this question, okay, suppose it is said that there is a magnetic dipole, okay, and you have to find the field at point A. Okay. So for point A, what is the value of phi? The value of phi is 0. Right? What is the value of theta? Because point A is in the xy plane, the value of theta is 90. So once you know phi, once you know theta, you can write an expression for the field of a moment m at distance d1, right? Basically this. So just try using this relation. So this is your expression for magnetic field at this point. Now there can be questions where you are supposed given, you are said that the field at this point is known. You have to find the field at some later point, right? So the field at this point is given as, suppose this is known. So that means you know D1 and you know the field. So you can use this relation to find M. Once you know M, you can basically use the same M to find the field at some other point. Okay. So for this point, suppose B, again, the phi here will be 90, right? And theta is also 90. So phi is 90, theta is 90. So this is the expression of magnetic field at point B. So if the field at A is given and the distance D1 is given, D2 is given, you can use this relation to find M. And once you know M, you can use this relation to find B. So there can be all these kinds of questions. Okay, so and there can be questions where the important point is here it's in theta cap. So you are writing it in terms of the spherical coordinates. if you are asked to find the field in the, or if the question has specified the field in the rectangular coordinates, then you have to use this relation. So long back in the first class, you remember we discussed about how to go from different curvilinear coordinate system to rectangular coordinate system, right? So this is what you have to do here. So once you know the field in the theta cap, phi cap, like in the spherical coordinates, use this relation to go back to the, you know, write the same in terms of the rectangular coordinate system. Okay. So if you have a small magnet somewhere at the origin, okay, and then the field is specified at some point given like this. So if we compare this question here, D1 is provided and you know the field given as -1 z cap. Okay, the direction of the field is given. It's along minus z cap. Magnitude is 1. It is asked what is the field at some other point B. Okay, where again D2 is given as 3. So now basically you can use this relation, whatever we just discussed so far, to actually find what the field at point B will be, right? So here, as you can see from this question, B is given as 1, D1 is given as 10. You have to use this relation to find M. Once you know M, for this question, you know M, you know D2 is 3. So then you can just use this relation to find what is the field. Okay, so that's how this kind of questions can be addressed. Okay, now as we just discussed in the last to last question, where we saw that in between those two planes, there was this medium with a different permeability. Now, what is this about? Okay, so where you can have different kinds of mediums with different properties. So just as when you had a, some material in an electric field, we saw that the charges got redistributed, and because of which you got a net polarization of the medium, right? So similarly, if based on what medium you have, inside the medium, if you have small current loops generated, right? So that can also generate a net magnetization in the medium. And based on what kind of matter it is, you can have different kinds of reorganization of the current loops, and that can result in either enhancement of the field inside the medium or reduction of the net field. Okay, so basically medium can get magnetized in presence of a field, or it can also have a net magnetization of its own. Okay, so based on all this, you can define the medium as diamagnetic, paramagnetic, or ferromagnetic. So this is the M. M is defined as magnetic dipole moment per unit volume. Okay, magnetization is defined as magnetic dipole moment per unit volume. So if you have a region, okay, what is the dipole moment per unit volume? And that depends on the permeability of the medium. Okay, so just as we saw in the last case where you had a medium where permeability was 5 times of what you have in free space. So that just means that the field lines get enhanced in that region. Okay, why is it happening? That is because of the rearrangement of the current loops that can get generated inside the medium. So for a diamagnet, what happens is when there is no external magnetic field, there is no net dipole moment. And when you apply a magnetic field, the moments, the loops that get generated, the moment that gets generated inside is opposite to the direction of the magnet, the applied magnetic field. And that's why the net magnetic field inside a diamagnet gets reduced. It is less than what you have applied or what is there in the surrounding. Okay. So basically, if you look at the field lines, this is how it will look like. The field lines will disperse inside the diamagnetic medium. They'll move away. Okay. So for this case, the relative permeability, if you define, will be smaller than 1. While you can have mediums like paramagnetic medium, where what happens when there is no magnetic field, there is no net dipole moment. But once you apply an external magnetic field, the moments align, because of which you get a net dipole moment per unit volume. So basically, the field lines, if you look at the field lines get concentrated. So the field inside will be higher than what you have applied outside, whatever is outside, right? So here mu r is greater than 1. You can also have medium which naturally has a net dipole moment. So there is some alignment of, of the moments inside naturally. Okay, so they even at zero external field, they have a net magnetic moment. And now when you apply the external field, these moments try to align so that they are in a more energetically favorable state, and they have a rearrangement and they get aligned towards the magnetic field that you have applied. So what happens here is that the field lines are, strongly concentrated inside a ferromagnet. So here the permeability is much, much greater than 1. Okay, so you can have all this different, these are very basic classifications. They can all be different kinds of classifications, but the primary ones are this. Okay, so that means based on M, the magnetization of the material, you can actually define the magnetic properties. So now if you have some medium which can have a net magnetic moment, okay, so you have some M, that means some dipole moment per unit volume is there. So because of this dipole moment, we saw that whenever you have a dipole moment, it can have a field due to the dipole moment, right? So now what is the field due to a magnetized object? So if you have a magnetized object with dipole moments inside, what is the field due to that? So for that, you can again start with the expressions of vector potential for a single dipole. Okay, so single dipole is given by this is something we just derived. Now for a magnetized object, you have moments per unit volume. So the net effect will be a volume integral. Okay. So if the magnetization is given as capital M, then M d tau has to be done. That's the dipole moment per unit volume. Like in the volume element d tau, the dipole moment is M d tau. And then you write the expression. So basically, this is the expression for your vector potential. Okay. So now there's some mathematical simplification that one can do. Okay. So this term here, r cap by r square, okay, can be rewritten as divergence of 1 by r, where r is the distance, magnitude of the distance from the moment to the field point where you want to find the field. And then you can use the integration by parts and use the, so here you can move from the volume integral to the surface integral using the divergence theorem and basically get an expression here. So this expression is important. This is telling you that now the vector potential due to a magnetized object has two contributions. One is like a volume current, another is like a surface current. And all of this is coming because of the magnetization of the material. Okay, it's not a free current carrying source that is giving rise to this vector potential. This vector potential is coming because of the medium property. Okay, so this is called the volume current, which is defined as curl of M, where M is your magnetization. And then you have a surface current, which is given as M cross N cap. So these two contributions, so one is this volume and the surface contributions, give rise to the vector potential for a magnetized object. Now, once you know A, you can basically find the magnetic field by doing a curl of A. Okay. Now, if you remember, these are analogous to what happened when we, spoke about electrostatics, where you saw that because of redistribution of charges, there was bound charges, right? So you had a volume charge and you had a like bound volume charge and bound surface charge, sigma b and rho b, right? Which depended on the p, that is the polarization of the medium. So similarly here, this volume and the surface currents depends on the magnetization of the material. So now that means you can rewrite your initial expression of Ampere's law where you had a relation that related the magnetic field with the volume current density. You can actually now write the contribution in terms of a bound current and the free current. Okay, and this bound current is given as curl of M, where M is the magnetization. So now you rewrite the term and you get something like this. Okay, so this term here is called the auxiliary field. So as you can see now, if you use this expression, so you get curl of H is equal to JF. So JF is the free current. Okay, so that means it does not. So if you look at just the auxiliary field, it takes into account the effect of the free currents that are there in the system. While if you look at B, it has contribution of both the free current and the bound currents that might have generated in the medium. Okay. Now, if you say that the magnetization is proportional, so in the linear limits, if we say that the magnetization is proportional to the applied field, this proportionality constant is here. Okay, susceptibility. And this term, basically now you can actually write a relation which relates the auxiliary field with the net field. Okay, B and H by this constant or this, proportionality constant. So this term here is the permeability of the given medium, which has the contribution, has taken into account the effect of the magnetic moments, the bound currents that might have generated in the medium. Okay. So this is your permeability of the medium. So now that means if you know H and if you know the permeability of the medium, you can actually find the effective field. So suppose in questions like this, where you have a long current copper rod of some radius r, which is carrying some current I, you want to find H. So if you have to find H, you just have to look into the free current that is there. Okay. You don't have to consider or bother about the medium properties. Okay. So then you can use your typical Amperian loop concept. Okay. So anywhere inside, if you consider a small loop, you have this current uniformly distributed in this rod, right? So basically, the small loop will enclose some current and it will be something like this. So H into 2 pi S, which is the line integral. You have taken a small loop and doing a line integral over the loop. So H into 2 pi S will be equal to I free that is enclosed. And that is nothing but I by pi r square, which is the current per unit area into the area, perpendicular area cross section, which is pi S square. So that means this is your field for any S less than R. So that is somewhere inside the rod. While outside, you will have the total current, whatever current is flowing through the rod, the total current will be already enclosed in the loop. So then the auxiliary field is given as I by 2 pi S, where S is the distance from the rod. Okay. Now, once you know H, if you know the medium property of the medium inside the rod, like suppose if you know mu for rod for copper, okay, then you can find, once you know H for inside and outside, if you know the mu, the permeability of copper, you can actually try to find what the field is inside the copper rod. While outside, because it's free space, you can just multiply by mu naught, which is the permeability of free space, to find the field. Okay. So anywhere in a medium where you have the permeability different from free space, you have to take into account the permeability of that medium and then relate the auxiliary field with the net field. Now, so if I go back, we discussed about this, so we discussed about how one can start from the divergence of B and the curl of B and go to this boundary conditions, right? So these boundary conditions will also be translated to the magnetization and auxiliary field components, right? So as you can see, because B above and B below are continuous, while the tangential components have this discontinuity, the same will be reflected in the auxiliary fields. Okay. Okay. So I think that's it. Do you have any question? If you have a particular question, you can ask me, or you can also write it in the chat box. So what we have discussed so far is basically we tried to look into how magnetic forces originate and how one can find the forces, the direction of the forces, when it can be attractive, when it can be repulsive, and all that. And then we talked about how the medium properties, the magnetic property of a medium can affect the field lines and how it has to be taken into account. Okay. The definition of auxiliary field, it just depends on the free current distributions. And then you can relate it to the net field, which has the effect of the magnetization of the medium. Okay. And we also looked at analogous things, how to relate, you know, so there's a huge similarity between how we started with electrostatics and dealt with electrostatics, and then how we moved to magnetostatics and dealt with magnetostatics, right? So this analogy that's coming up again and again. So we looked at that, and now we know that if you know a current, if you have a current distribution, how to find the field, how to find the vector potential, and then from there find the field. Okay. So we discussed all that today. Uh, there's no doubt. Let's call it a day. Thank you. Thank you.